So now we can start with the actual program. So I'm very honored to invite Claudia Diaz to the podium. Claudia Diaz is a chief scientist at NIM Technologies and also an associate professor at the Department of Electrical Engineering at the KU Leuven. And for the last 2 decades, Claudia has worked on designing and evaluating privacy technologies with a major part of her research focused on traffic analysis and anonymous communications. Since 2019, she's one of the main contributors to the design of the NIM network, which is the thing you're going to present now, right? So the NIM network and the next generation of privacy infrastructures. Let's give a warm welcome to Claudia.
And for the slides? Perfect. Well, thank you very much for the invitation to this very fancy place. And I am very happy to be able to present the work we are doing in NIM. So to give you a short outline of the talk, I will go through 4 main parts. First, I will talk about the different approaches to communication privacy in order to situate mixed nets in the solution space to communication privacy. I will then introduce the NIM system, so what is the overall design and what are the components. I will then move on to talk about the economic model and incentives, because this is an incentivized system. And I will finalize talking about the current status and the ongoing work that we're doing, because we're still doing more things. Okay. So just to introduce the problem of network privacy, I mean, as you all know in this room, a lot of really great work has been done over the last decades, and today we have modern cryptographic protocols and algorithms that offer very good protection for data and transactions. We can encrypt messages end-to-end in ways that are very difficult to decrypt. And we can do transactions that have privacy properties, such as protecting the sender of the transaction or the amount in the transaction and so on. Now, all of these protocols, they are run by parties that are in different locations and that use public networks such as the internet to communicate with each other and exchange these messages in the protocols. And the issue is that the network level metadata of these messages is exposed by default by internet protocols, by TCP/IP. And is exposed, and a lot of parties have access to this metadata because there is a lot of intermediaries in the infrastructure, from the Wi-Fi provider to backbone operators that have access to the metadata that is exposed. So what do I mean by metadata? Is who's sending the message, who's receiving the message, how long is the message, what time the message was sent, and then when you have full flows, there is data flows and data patterns in the flows, such as, for example, do you have bursts? How long are these bursts? Do you have some sort of patterns that are recognizable in the back and forth messages that are being exchanged? And when you start analyzing this metadata, meaning the number of packets, their timing, their volume, and so on, this can actually be very powerful in revealing private data that is protected by the cryptographic protocol. And there are some really good examples. So for example, when you're using TLS to access a page in a website, the encryption protects the content of the data such that nobody can see which subpage you're accessing. For example, if you're going to some medical database, WebMD, you're checking a disease, people can see you're checking this website, but they cannot tell which specific page you're looking at. Now, there is this technique called fingerprinting that basically would allow an adversary to go to this website, download the different pages, look at the different patterns, so how many bytes are sent back and forth for each of these pages, such that when you are accessing the website, by looking at the number of packets sent, the timing of these packets, it is possible to infer which specific page you're looking at, even if the cryptography is perfect and cannot be broken in order to read the content. There is also examples, for example, with encrypted voice over IP, very, very nice work a few years ago, where they showed that the use of variable bitrate codecs and length-preserving stream ciphers allowed to actually decrypt encrypted conversations just by virtue of doing traffic analysis and then processing those data points. So if we want to have network privacy, what does it mean? And it's not just one property, there are many different properties we might want to have. So we might want to be a bit more fine-grained when talking about network privacy. So obviously content protection is the first thing, but this is kind of solved already by kind of cryptographic algorithms. So the weakest or the most simplest privacy property you can have is third-party anonymity. This is the case when, for example, you're talking to a trusted party, you're talking to your bank, you're talking to your lawyer, you're talking to your friend. You want to authenticate each other. You don't want to be your bank to be anonymous to you or anything. You want to know that you're talking to the right person, but you might not want other people, other parties in the network, to know that you are having a communication. Okay, so you're having anonymity towards third parties that is not the one you're talking to. Similarly, you can have sender anonymity. This is when you want to talk to a recipient to whom you don't want to reveal your identity. So this is very simple cases in web browsing. You're browsing to a page, and you might not want to reveal who you are to this website because you might not have a pre-existing trust relationship with them that makes you want to identify. And a bit more tricky is to have recipient anonymity, which means that you want to be contacted or reachable without revealing your network identity. When I'm talking about identity here, is network identity, meaning IP address. So you want people to be able to get information that reaches you without them knowing where you are. In the context of Tor, these are what I call onion services. Different kind of properties that don't relate to who you are, but other things we might want to conceal is, for example, unlinkability. This can relate, for example, to clustering. So maybe I don't know who you are, but I can tell that these different transactions were done by the same person. This might be desirable in some cases when you want to have some sort of persistent identity, but in other cases this might be undesirable, and it's important to realize that when you have a lot of linkability, this can undermine anonymity. So maybe I cannot trace who you are based on the network connections, because there is, like, for example, very good third-party anonymity, but I might be able to start learning more about you if your identity is very persistent. So you're the person who was in Abu Dhabi, who was checking an Abu Dhabi hotel that is having a conference and was checking, the name page and was checking this and this and that. If you start putting things together, you might actually start being able to infer a little bit better who this person is. So to prevent that, you might want to have unlinkability. In the context of financial applications, this means that when a person does different transactions, you don't necessarily are able to see that these transactions were done by the same party. If we move to properties that are kind of trying to protect even further the usage of your protocol exchanges and usage, we come to unobservability, which is concealing when you're communicating and how much you're communicating. So volume and timing of usage of the system. This typically involves the use of dummy traffic, meaning that you are kind of doing things even when you're doing nothing, so that it's not possible to determine if you're doing something or not. And even beyond that, we can have undetectability, which is that it's not possible to determine whether you're using the system at all. Now, this is really hard, undetectability. This is kind of another whole range of techniques of making it possible using steganography and techniques like that, so that it's not possible to see whether somebody is using the system at all. In terms of terminology, not everybody uses these words, so sometimes people will use unobservability to mean what I mean here by undetectability and so on. So there is not such a canonical kind of terminology, unfortunately. So who is your adversary? You want to have these properties against whom? So typically, the first adversary that is considered is the network adversary, because, as we said in the beginning, the problem here is that parties are communicating, and they are doing so over public networks, and these public networks might have some malicious parties as intermediaries that can kind of try to exploit the metadata they have access to. So when we have an adversary model, I mean, in cryptography, you typically have Alice and Bob, and the adversary in the middle, and that's it. It's very simple. Here you have to be a bit more fine-grained. Is this adversary able to see the full network, all the communications in the network, or maybe only some of them? So for example, maybe the adversary is just your local ISP provider. It can see your communications, but maybe not other parts of the internet. Or maybe it's the recipient, or maybe it's somewhere in the middle. Now, because these systems typically introduce new entities, you also have to consider what happens when some of these entities are corrupt. And this includes either intermediaries that are assisting in achieving network privacy, or the correspondent that you're talking to, like the sender or the recipient. And one thing that is different in this kind of techniques from cryptography is that the method here is typically statistical analysis of metadata. So meaning that the adversary is going to be collecting, packet timings and packet sizes and so on, and will be trying to infer statistically interesting things about what's going on, who sent it, are these two transactions related, and so on, trying to violate the network privacy properties. And that also means that the properties that you achieve are typically probabilistic, so it's not quite as strong as the kind of properties you get with crypto. Okay, so a lot of work has been done over the last decades in trying to find solutions to this problem. So if we go to the simplest ones, it's just the trusted third party, right? So in this case, the trusted third party solution is the VPN, meaning that instead of communicating directly to your recipient, you just have an intermediary server that will relay your communications to your recipients. So very simple solution. Of course, with respect to the adversaries that we just mentioned, this protects you if your concern is just the recipient. So if you don't want the recipient to know your IP address, a VPN solution will achieve that. Or when your adversary is your local network provider, you will also achieve what you want, because the local network provider will see you connecting to the VPN, but they basically cannot really learn much more beyond that. However, if the adversary is able to see, for example, the VPN server from the outside, the input-output connections of the VPN, they may be able to correlate incoming and outgoing streams, and therefore link the sender to the receiver and violate anonymity properties. And obviously, if the VPN provider itself is malicious, then you have no privacy whatsoever. You actually have made it really easy for them to learn everything about you. Okay? So more sophisticated solutions, such as onion routing, that was already proposed in the 90s and has been implemented since the early 2000s in the Tor network. It uses not one intermediary, but several intermediaries in a chain, typically 3 of them. Right? So in this case, you basically select a path over a chain of relays, and then they forward the communication to your recipient. So in this case, if one of the intermediaries is corrupt, you're still safe, because they are not able to violate the network privacy properties, linking sender to receiver. If your recipient is corrupt, you're also in a good place, because the recipient cannot trace back the communication to you. Same for your local network provider. So Tor provides stronger properties than VPNs, particularly because it distributes the trust over multiple servers compared to one. However, if the adversary is able to see like the full network, then they are still able to correlate connections. Mixed nets that were already proposed in the 80s by Chaum, so they are also quite an old technology, and we have different implementations. They also follow a similar approach, so intermediary servers that forward your communication, and in a moment I will go into looking into the differences between mixed nets and onion routing. So I'll get to that in a moment. And we also have other designs, such as peer-to-peer designs, overlay peer-to-peer. So some of the early designs are also from the 90s. Some of them have been proposed very recently, such as Dandelion. The difference between these designs and onion routing or mixed nets is that here the users themselves are the infrastructure. So you don't have this distinction between clients and servers, some people using the system, some people providing the system. Here, every user is both a user and a provider for others. And finally, we have also quite classical technology, DC nets that are broadcast-based instead of kind of choosing intermediaries for relaying. There are different. The original flavor is very peer-to-peer. Some more modern designs. They use client servers to make things more efficient. But the problem with DC nets is that they have a huge communication overhead, in the sense that for one person sending a message, like everybody else has to send a message as well. So that's a huge overhead, even more than the overhead that we have by relaying communication through 3 or 4 intermediaries. And they're also, even though they provide really nice theoretical properties, in practice they don't deal so well with churn and with parties failing to send the messages when they have to. Okay, so, sorry? So I will now go a bit more in detail into these different designs. So they all have multi-hop routing, so they use a chain of intermediaries. Of course, DC nets is an exception. They are overlay networks, so meaning that every arrow that you see on the top figure is actually a full end-to-end connection in the internet. So that means that they are compatible, they are on top of the current infrastructure. There is also research on future internet to protect at the lower level. But this would be, of course, great and more efficient, but this requires buying and changes from the infrastructure, which is not so easy to obtain in practice. And they typically have per hop bitwise unlinkability, meaning that the input and output of each of these, in each of the intermediaries is going to look different, and they use like this kind of nested encryptions to achieve that. There are exceptions for hop-by-hop routing. In hop-by-hop routing, basically, the sender does not determine the full route of the message, but only sends to one successor, and this successor decides on the rest of the path. In this case, you have a weak form of anonymity, because since everybody has to be able to reach the final destination, that means that they should be able to see the final recipient, and therefore, the privacy is given by the fact that you don't know if your predecessor is the originator or a forwarder, but that's kind of a deniability property. Okay, so looking a bit more into the differences between peer-to-peer overlay and client-server architectures. In client servers, we have this distinction of roles. We have clients and we have infrastructure. And then we can have different requirements for these parties. We want to have privacy for clients, but we want to have transparency from the infrastructure. We want to know that these servers are forwarding the packets as they should, and they're acting honestly, following the protocols. In peer-to-peer, in contrast, there is a merging of roles. So clients make up the infrastructure. So here you can have a tension between privacy and transparency, in the sense that when you are forwarding my message, if you are also a client, I might want to check on you, and that might reveal things about your own activity. They're also having challenges with reliability and churn and quality of service and competency, because you have end users effectively running the infrastructure as opposed to more professional kind of providers. In client-server architectures, typically you need to have full knowledge of the network, because you're selecting this path through the set of servers. So this can be a scalability bottleneck that you have to keep an updated state. Of course, this gets worse if you have a very high churn of nodes. If it's a very stable network where the keys are updated with some frequency, but that is not too high, then this is not such a big problem. There's solutions as well to try to reduce this overhead. In peer-to-peer, there's the two flavors. Some of the systems have also require full knowledge, such as Lightning Network, for example. So that can even be more of a problem with scalability. And some others, they say, okay, you just need to know a few peers, and then you can already use the system. And the problem is that this introduces vulnerability to Eclipse attacks, where you kind of poison the views that different clients can have. The main thing from an anonymity perspective is that in client-server architectures, you have what I call thick traffic per server. If a server is serving thousands of clients, it's aggregating traffic from thousands of clients, and that means that it's acting as a hub, so it can create very large anonymity sets. And there is this famous quote of Anonymity Loves Companies, a paper by Dingelman. In peer-to-peer, on the other hand, there is thin traffic per server, meaning that because the system scales with the number of users, in the end, the amount of aggregation that you have per peer depends on the path length rather than the number of users in the system. And we have some recent work on NDSS that shows that deployed systems such as Lightning and Dandelion actually provide very low anonymity precisely because of this thin traffic. Okay, so what's the difference between onion routing and mixed networks? In onion routing is circuit-based. So that means that the client first establishes a circuit, doing handshakes with the intermediaries in the path, and then that establishes some symmetric keys, some session keys, and then all of the packets are processed with these symmetric keys. So this is very efficient on the good side. On the bad side, you have linkability of all the messages within the flow, right? Every intermediary knows that all of these messages belong to the same flow. That enables things such as fingerprinting. And if you want to use dummy traffic, it's very difficult to come up with a scheme that is going to pad flows effectively, because these flows have such rich features when you have a long flow with lots of messages. Mixed networks are packet-based. So that means that every packet has an independent route. So that means that every packet needs to be processed with public key crypto. So that's much more expensive. On the upside, you have a linkability between any two messages within the same data flow. Okay. If you use dummy traffic, here is much more effective, because the fact that every packet is kind of independent from the others. If I am sending dummy traffic to the system and we are routing our traffic through the same intermediaries, my dummy traffic will also increase your anonymity, which is not the case when you have, this per flow distinctions. In onion routing, there is no added latency, so every intermediary that receives messages just forwards them as fast as possible, and that makes the system vulnerable to end-to-end correlation attacks, where you look at the features of flows, and then you try to correlate them, and fingerprinting attacks, which are just on the client side. In mixed networks, on the other hand, this is where the name of mix comes from. Basically, each of these entities will add latency, which creates a reordering of messages, so you cannot no longer correlate first in, first out. Now, some messages come in, some messages come out, but the correspondence between input and output is difficult to establish, not only cryptographically, but also in terms of timing and order. So here there is, of course, a trade-off between anonymity and latency. The more latency you add, the more anonymity you can get. But of course, it makes the system less usable. If you have more clients, the trade-off is better, because then you can aggregate in larger anonymity sets with a lower latency. So finally, the onion routing is built to protect against local adversaries, while mixed networks are built to protect against global adversaries. Okay, so NIM is actually a mixed network precisely for these reasons. We are trying to build a system that can protect against global adversaries. All right. So let me introduce the basic design. It is based on Lupix, which is a paper that was proposed already in 2017 by Piotrowska and others. And it inherits many of the design choices of Lupix. These are, it uses the Sphinx packet format, which is source routed. So that means that the sender chooses the full path through the network and builds packets with multiple headers, one per intermediary. There is a group element in the beginning used to derive the key that then decrypts the rest of the packet and can check the integrity. When the intermediary decrypts the message, it finds which is the next hop that it has to be sent to, and then processes the packet cryptographically to make it completely different and unlinkable from the input. It's a layered network topology, so that means that it has specific structures. So you have a set of entities that are in the first position, set of entities in the second, set of entities in the third. This topology has certain advantages towards others. So with respect to cascades, which was, for example, the original designs proposed by Chaum in the 80s, is that it can scale better. So you can add more layers, more rows to this network, and then have more users, and all of them will be part of the same anonymity set. If you have cascades and you hit the limit, you have to have a new independent cascades, and then these two anonymity sets will be disjoint, right? And with respect to free route, which is that every combination of every order and combination of intermediaries is possible. I mean, I can go into this in details in the questions if you want, but actually this provides slightly better anonymity, and it also makes it much easier to have things such as load balancing. So the original mix that some of you might be familiar with, it basically takes n messages, decrypts them, and then reorders them and outputs a permutation. This is not how the system works. This is based on continuous mixes. So basically, the client, for every hop in the path, will draw a sample from an exponential distribution. Okay? This exponential distribution is the latency per hop. It has a mean, and you draw a sample, and you encode this latency in the Sphinx packet header. When the intermediary decrypts the packet header, it will keep this message for the specified time and then forward it. The effect of this strategy is the same as having what is called a pool mix, meaning that once you have, let's say, n messages in the mix, and one of them goes out because of the memoryless properties of the exponential distribution, all n messages in the mix are equally likely to be the one that was output, regardless of when they got in. In addition to having the nice property that instead of having a batch that has kind of disjoint anonymity sets, here you have a kind of a continuous stream, such as that everybody can be everybody else, and you kind of aggregate, have better anonymity. You can also adjust mean latency per application. So it makes it possible to have different latencies per application, as opposed to batch systems where you have to wait for n messages to arrive in order to forward something where the latency is not bounded. Okay? And in addition to that, it allows us to have reliable transport, because I can predict when my message will be delivered. We have a way to send back an acknowledgement using what is called a SIR. This is a single-use reply block. And this is basically a set of headers. I have created a sender that is basically a path that points back to me. So I give these headers plus the first mix that has to be sent in the first layer, plus some set of keys to process the payload. And then the recipient can create a payload, attach it to these headers, send it to the mixnet, to the first mix that I specify, and then the network will route things back to me. So because I am the sender, I'm encoding all the delays of the forward packet and all the delays of the acknowledgement, I can have an estimation of when I should see this acknowledgement. And if I don't receive it, it means that the packet got lost or the acknowledgement got lost. Okay. And then finally, for sending, there is a Poisson sending process. So that means that the client draws a sample on when should I send my next packet. If they have a real packet to send, I'll send the real packet that I have to send. If I don't have a real packet to send, I'll send a dummy packet that is going back to myself. Of course, having more dummy packets is more overhead, also more unobservability. So there are trade-offs here between usability, overhead, and observability. Okay. So NIM is not only a mixnet, but it's incentivized. So why do we need any incentives? So the main reason is scalability. Okay. So a lot of these systems that were proposed over the years were then run as volunteer-operated networks. This is very nice, but the problem is that there is only so many people that are willing to put their time and resources to provide a service for others. Tor has shown that this can scale to a few million users, but whether that can scale, that model can scale to hundreds of millions of users is another question. So the idea is that the idea is to basically turn it into like any other service where you have people that use the service and pay for it, and people that provide the service do some work, and they get paid for the work that they do, right? So the idea is that if you have a paid system, when you have more users, you have extra income, and this extra income you can use to pay more servers, add more rows to this mixnet, and have more capacity and be able to serve more users. In the case of volunteers, you don't have a guarantee that a surge in users is going to lead to a surge in offer. You not only want to scale, but you want to scale with a good quality of service, right? So peer-to-peer architectures where all users are also infrastructure are proposed precisely because they can scale quite naturally, just as more users join the system. But if these users are working out of laptops, out of phones, they are online, offline, it's very difficult to have a system that works reliably and that offers a good quality of service. So instead, we prefer to distinguish between professionalized providers that do a good job and they get paid for it, and then consumers that get a good service and are also willing to pay for it. So what is the goal of having these incentives in the mixnet is to be able to have a sufficiently big system that can serve all the demand. So what is sufficiently big? Well, that you can basically have all the throughput that you need for handling the traffic load. And also, we would like nodes to compete on quality. So if you have too many of them, then you want to select the best ones, because you don't want to have a network that is too big either. Otherwise, you start having this thin traffic problem again. You want the traffic to be, these hubs to be kind of fat enough that they produce good anonymity sets. So if you have an excess of providers willing to participate, then you can select the best ones. All right, so just to walk you through some of the kind of flows in the system, I have to say this is not yet, this is implemented, most of it is implemented. The DKG is still in works, but the rest is implemented, but it's not yet, for now the service is for free. So this is not being activated yet. This will be probably sometime next year. So how do you handle the private service payments? We do it with credentials, anonymous credentials. So the idea here is there is you. I mean, you don't see the mixnet here because you haven't yet, you are still registering for the system, and you do that with the validators that are basically running a blockchain that records transactions, and then you have these other entities, which is the gateways, which are acting as interface between the clients and the mixnet. Why? Because we don't want to the mixes are basically receiving strings packets, decrypting and forwarding. We don't want to burden them on top of that with having to check credentials, keep track of users, how much traffic they spent, and so on. Also because we want to have this mixnet being dynamically reassigned. So you would have to have a constant first layer if you want to have clients kind of directly interface with the mixnet. So gateways are basically there to check credentials. They can also, there's the possibility of bundling other services, such as, for example, they can store things for you. Maybe they offer censorship circumvention capabilities. And also, it limits the exposure of your IP address. The gateways, the mixnet path is actually chosen automatically by the software, but the gateway is your choice. You choose your provider. If you think about in models, you can have this gateway be actually the VPN provider, for example. Or you can have people run their own if they wish. So how does this work? So first, the user makes a deposit into a smart contract and generates an unsigned Coconut credentials. So we're using Coconut credentials that were proposed by Sonino and others a couple of years ago. So you generate the credential that says, oh, there's a deposit for a subscription for a month, and I know the private key of this deposit. So then the validators, they check that the proofs are correct, and if everything checks out, then each of them signs a share of this credential. So the difference between Coconut and other credential systems is that it has threshold issuance, meaning that you don't have a single issuer signing the credential, but you actually have multiple issuers that each of them sign a share, and then you can aggregate those shares into a complete credential, into a functional credential. So that's the next thing that is done by the client, aggregates enough shares to reconstitute the credential, and then you re-randomize the credential in order to make it unlinkable from the shares that were issued. Okay. Then you spend this credential with a gateway of your choice to buy access to the system. This credential is redeemed by the gateway, and there is a double spending check that this credential was not yet spent. You didn't go to another gateway to register, and you kind of double spend your subscription. And then this gateway will receive, so gateways are also incentivized, and will receive a part of the fee that was paid by the user. The other part is reserved to pay for the mixnet. So part of the service is provided by the gateway, some by the mixnet, so the money is also divided. Part goes to the gateway, part to the mixnet. The validators, they are incentivized by transaction fees in the blockchain. Okay, so once this is complete, you have a subscription you can use. I mean, this is, as I said, the service is for free right now, but the idea is that you will be able to have, for example, for the next month, you have up to maybe some daily limit of traffic or bandwidth limit. Okay. There is a demo, a very nice demo, if you want to check out how it works. So now you are subscribed, you want to send traffic to some app or service. So the idea is that first you create your Sphinx package, so you will have a data payload that has to go to some destination. You will select randomly, with local randomness, a path through this network, and also delays for each of the hops. And also you will generate an ACK that will be coming back to you that you include with the payload. There's multiple encryption layers, so you first encrypt for the end recipients, then you encrypt for the recipient's gateway, then the 3 mixed nodes in reverse order, and then finally you have a kind of a session key to communicate to your gateway and protect that connection. You send the packet when the timing is right, according to the Poisson process. The gateway decrypts the packet with the session key and forwards the packet to the mixnet. Then each of the mixes in the route processes this packet, basically decrypts the Sphinx header, keeps the packet for the specified time, and then forwards the decrypted packet to the next destination. And then this is at some point routed to the recipient's gateway. The recipient gateway obtains 2 things. First, the payload that has to be given to the recipient, and the ACK to be sent back to the mixnet. So why do we have the ACK sent to the gateway and not to the recipient? Because this way we can have recipients that are not online, and we still have, guaranteed delivery. The gateway is supposed to be always online. The recipient can come back later, pull the messages from the gateway, and receive your information. What you want to know is that it got delivered to the gateway that is going to keep information for your recipient. Okay? And then, the recipient retrieves the information while the ACK is sent back to you. If you don't receive the ACK, well, then you will have to resend. Starting from the beginning, you have to create a new fresh packet. Okay? So that's the flow. So we have collected some payments from these users. Part of it went to the gateway. Part of it has to be allocated to these mixed nodes. How do we allocate the payments to the right parties in a decentralized manner, right? So to do this, we actually borrow concepts from proof-of-stake systems. In this case, the proof-of-stake is not for the purpose of a consensus, but it's actually done in a smart contract, but it's for the purpose of managing the network, so deciding who is going to offer the service and giving them the appropriate payment, okay? So we actually conceptualize a stake as reputation. Okay, so the reputation of a node is signified by the amount of stake that has been allocated to that node. And this is both the operator's own stake, which we call the bond, and delegations from other stakeholders that are supporting this node, that believe that this node is a good provider and they want to support it. Okay. The way the stake is not, there's a stake saturation, so it's not like the more stake the better, it's up to a point, right? This point is determined basically by the amount of stake in the system that can be staked, divided by the number of nodes that you want to have to provide sufficient throughput, right? So that defines the stake saturation point. Beyond that, you don't want more stake to over-concentrate on nodes because you want to have at least so many nodes in order to have enough throughput. So you want to discourage over-concentration. Okay, we want to, so these stakeholders that have some stake, that they can delegate it to nodes, we want this to be useful to the network. We want them to allocate to the best nodes. So what are the best nodes? Mainly is the history of reliability and performance. So you want nodes that have very high uptime and no packet loss. You also want cost effectiveness. The pricing is set to cover costs. So you want the service to be affordable. So if somebody is able to provide the same service for lower costs, this is a good thing. And we also have a premium for people who put skin in the game. So if the operator's stake is larger, that is going to increase somewhat the rewards that are received by that operator. This also has an effect of penalizing civils, meaning that if you have an amount of stake and you divide it into multiple nodes to run more nodes, you will get fewer rewards than if you put everything on one. Okay? Unless you have more than the saturation point, at which point you might want to run two of them. So then so now we have a set of nodes, and they have some stake. And when I think about stake, I think of it between 0 and 100. So as a percentage, this is 100% saturated. This is 50% saturated. So okay, so you have, because it's maxed out. So if somebody has more than 100%, it's still 100%. So what we do then is that we sample these nodes according to reputation. So if I want to sample 240 nodes, for example, as we do now, and we have 500 of them, I will basically just flip random coins proportionally to the reputation until I have selected the ones that I need. This is done hourly. The hourly resampling is also done so that if a node is down, it doesn't harm the network for too long. And the idea here is that because there is a limited supply of stake, then the nodes are competing for stakeholder support, so that you have a reputation system that makes sense, because it's not like the reputation can be increased infinitely or something like that. Okay, and then once some nodes have been selected to provide the service, then they will be rewarded, and they will be rewarded according to how much stake was in them, but also, very important, according to their performance. Performance as percentage of packets processed. So did they lose any packets? If they lost packets, they will get lower rewards. And then the rewards are shared between the operator and the delegates. So if I am delegated to a node and this node has low performance, I will have an opportunity cost that I will be receiving fewer rewards than if I allocate my stake to a better performing node. So basically, we see here that in this kind of a staking system, as delegator, I am doing some job, which is basically selecting good nodes to provide the service. If I am doing my job better of this selection, this delegation, if I'm doing my job better, I will get rewarded more. If I do a really bad job and I delegate to nodes that have really terrible performance, I might not get any rewards at all. Okay. So what's the economic model? Let me start from the stakeholders in gray. So stakeholders is anybody who has any of these tokens. They can do two things with the tokens. They can stake them on nodes, either setting up nodes and bonding them, or delegating to nodes run by other people. So this is one thing they can do. And they can also spend the token on accessing the service, on getting a subscription for sending their traffic via the mixnet. So this token that has been spent on the service, this is the income from fees. Part of it will be blockchain transaction fees that funds the validators, and the rest is the fees for the bandwidth that you're paying. Part of it goes to the gateway that you selected. So your gateway, other gateways don't get paid, only the one you selected from your money. And the other part goes to this budget that is the rewards for the mixnet. So this is like a central casa that will then allocate money to the different providers, right? So this budget for rewards of the mixnet, that is on an hourly basis, It receives the income from fees when the fees are turned on. This is not the case right now. And it also has income from this mixed mining pool. So this is basically a bootstrapping reserve. And the bootstrapping reserve, the point is that you have a chicken and egg problem otherwise. An anonymity system is attractive when you have many people using it, right? But how do you get too many people using it if you're charging them in the beginning and it's not so good in the beginning? So how do you solve this problem? So this is how what this pool is about. It's actually 25% of the total supply is locked there, and every month there is 2% being made available for the budget. So 2% means it's kind of declining gently. It never really goes down. You see that there is also arrow going back. The budget is not always completely distributed. So you have this budget for this hour. Right now is like about 7,000 NIMs per hour. It doesn't mean that you're going to allocate all the budget. You only allocate all the budget when you're in the equilibrium, meaning that you have all the stake is perfectly allocated to the perfect number with fully saturated nodes that have perfect performance, right? If you're not having the full reputation of the nodes that you selected, if there is a performance that is not 100%, then not all the budget will be allocated. And the budget that is not allocated goes back to the reserve so that it can still sustain the system in the future when the performance is better, right? Okay. So just to give you sorry. Oops, back. So yeah, the budget, the rewards are then given to the mixed nodes, and then the stakeholders receive their share in the last arrow. Okay. So some graphs on because we have a deployed system, a deployed mainnet. So we have currently we have a mixed net is configured for 240 nodes, so that this is 3 layers of 18 nodes per layer. Currently, we have about 480 candidates, so roughly double what we need. And the current saturation level is 430,000 per node, and it's going to be updated like today or tomorrow because there is more stake available, and when there's more stake available, the saturation point goes up. This is how the graphs show how the stake is distributed. That's the bonds. So you see that, some people have high bonds. Many of them have small bonds. The minimum bond is 100 NIM, so it's actually quite cheap. And that's the distribution of delegations, the green line there. And as you can see, well, we have a few nodes that have pretty good reputation, and then it declines. Okay. So how likely is it to select you if you have a node? How likely is that you get selected to provide the service? Of course, it depends on your reputation, and it depends on the full distribution, right? So with this current distribution, if you have more than 25% saturation, you will be selected basically all the time. If you have less, then, well, it declines, as you see in the graph. Does this work? Do we have any correlation between reputation and performance, right? What was the result? So nicely, we see that indeed, when we look at, so in this graph, you have performance in the y-axis and reputation on the x, and you can see that the ones that have low performance all have very low reputation. Okay, so the nodes that get actually selected according to this curve are actually decently performing nodes. So in that sense, we see that it is working in the sense that people are putting their support on the better nodes. These are the kinds of rewards, so it's kind of linear with the reputation, and then maxes out after saturation. So if you're oversaturated, you're not going to get more. Currently, of the 7,000 that are available, NIMs, about 2,000 are allocated, and 5,000 are saved for the future. And in terms of returns for the delegates, it's very high right now. It will go down as the saturation point goes up. It's about 50%. You can see that it's roughly in the same neighborhood if you're having a node that has reputation that is not negligible. But if you're staking on an oversaturated node, we have 4 of them oversaturated, your returns actually go down. Okay. So what is currently available? We have a blockchain. It's called Nix, and is maintained by a set of validators. This is a Cosmos chain based on the Tendermint BFT, and it's actually a smart contract platform to which we have added the credential SDK, so that everybody can use it, and actually is open to anyone. So the NIM contract is just one of the contracts that is running there. Right now is the only one, but others might want to use it for their own projects. We also have a wallet that enables the stakeholders to keep their tokens, transfer tokens, bond nodes, delegate to nodes, and receive rewards for their bonding and delegation. We have the NIM Connect SOX5 proxy that is already set up to work with Telegram, Keybase, and Electrum Wallet. And it's very easy for any application that is compatible with SOX5 to basically tunnel the communication via the proxy. There is also a WebAssembly client for browser and web applications, and any. And then we also have a lively community, 13 languages, and groups in Telegram, Twitter, Discord. That it includes enthusiasts, operators, and so on. A lot more is still going on, so we have a lot of work ahead of us. We are very busy trying to improve the efficiency, usability, reliability, and scalability. This is also why the system is not yet paid, because it's not quite there at the point where you can really ask people for money for the kind of quality of service they get. So, for example, we are updating, as I said, today or tomorrow, the contract so that the queries are much more efficient and consume less gas. We are revisiting the mixnet parameters, so what are the packet sizes, latencies, and sending rates that we should set for given applications. We are looking into how to increase throughput with bursty traffic. So if you have a very constant sending rate, it's difficult to handle bursts, so maybe we need to have adaptive sending rates. Of course, this will come with a trade-off to observability, so it's a big world of trade-offs that we need to explore. We are looking into scaling, making the gateways and the services at the other side scale better with the number of users. Right now, they have some bottlenecks. We are changing the Sphinx packet format so that it's faster and nodes can do more of them per second. Looking into schemes for anonymous replies for large downloads, so you can send these serbs to receive anonymous replies, but if you need a lot of them, you need some sort of protocol to send, see if you got enough, and so on. Or we're also exploring anonymous drop boxes as an alternative if you have like high latency tolerance. Of course, very important to have integrations with applications, wallets, browsers, all kinds of applications. An anonymous communication system by itself doesn't really do anything. It's there to basically then serve applications that then people can use. We are still working on the distributed key generation for the anonymous credentials. The rest is quite ready already, and that will enable the paid use in the future. Fully decentralized performance measurements. Right now, the validators are checking on the performance, but in the full system, this is a big piece of work I'm actually working on with Angelos Kiayas, is to have a system where everybody, all the participants are kind of checking each other, and everything is verifiable to see that the performance is adequate. And we would like to look into gateways with sensors in circumvention so that it's difficult to block access to the system. This is a whole other topic that we want to get into. Bunch of links. If you want to know more, I will put the slides online so that people have them at hand, code, product, resources, and so on. And just to come to the conclusion, to the summary. Mixnets are a type of solution for network privacy that is designed to resist global network adversaries. So this is one of the main differences with Tor. It's incentivized, NIM is incentivized, and that tries to create a market for private bandwidth that can scale to serve demand. We leverage staking and stake delegation to have this kind of not reputation concept that then determines who participate, who are the people providing the service and how much they get paid for it. So that, the rewards and the participation are proportional to this reputation, and the scheme is done such that it promotes quality of service and cost effectiveness. We have a running mainnet with several hundred nodes that are competing for participation, and the anonymous credential system is also a big part of the system we are creating. So we have a basic functioning system, but of course a lot more in the pipeline that will come up in next year or two. So thank you very much for your attention. I'm happy to answer your questions.
Thanks, Claudia. It was a very nice talk. See, we have already hands up.
I think that your idea of fees is, may have made sense a few months ago. So there's a very famous case of asking for fees, and that's Elon Musk taking over Twitter. At the moment he changed the economic model, he had to fire 50% of his employees. Facebook is now going to do the same, similar things, laying people off. And not only that, at the moment he charges fees, major advertising companies decided no longer to advertise on Twitter. And the situation is that bad that actually Elon Musk is talking about having Twitter go bankrupt. So I think that your talk was a nice talk, but it's not up to date. Thank you.
Okay, so I don't think social media is a good analogy here. This is basically like a VPN service, and millions of people pay a few dollars a month to have a VPN. So this is basically a different design for a service that is very similar to a VPN that people are used to pay for. And that if you want to have, a network privacy access, you just pay your monthly fee and so on. I don't think social media is a completely different type of application, right? I don't think it is related to this.
Thanks for the nice talk. One quick question. So is there a way to measure or to monitor whether the mixed-net nodes are following the protocol? So, for example, not changing the delays or something like that?
Yeah, so whether they are respecting the delays, it's still doable, but a bit more tricky. The thing we're focusing more is packet loss. So are they, the thing is that if they are corrupt, respecting the delay does not become the main thing because they will already record this packet is this packet, right? Regardless, so not having a delay would just benefit a network adversary they are working with, but it doesn't really make a difference in the learning of the adversary, right? Now, for packet loss, it's basically like a secret shoppers scheme. Right now, only a few entities are generating these messages, which is validators. So you basically route Sphinx messages. The mixers don't know that this message is a measurement message or a normal message. And then basically at the end, you see how many of them arrived, how many of them got lost. In the full scheme, which is, I'm happy to talk about, it's a really very cute piece of work. There you are able to actually determine in which link things got lost. And then that allows you to kind of statistically determine who is not performing adequately. Yeah.
Is there any other question?
I have a comment about the exchange of ideas between you and Ivo. You said that millions of people are paying for VPN. If you look at the statistics of why people are willing to pay, it is not so much in order to have a guaranteed anonymity against everyone. It is in order to consume movies and other contents which is geo-restricted. So they want to look as if they are in the US in order to watch certain movies. So you have to be very careful in saying that people are paying a lot of money for VPN because they want the anonymity. They want other things.
Yeah, I agree. It's not the only reason, but I think that some people do want to protect. They don't want their communications to be. Also for censorship resistance, right? Which is something that we also want to.
Okay, so another comment about the censorship. You describe in one of the last slides techniques that you want to implement. In many cases, the very fact that you want to use any kind of anonymity service in some authoritarian countries will mark you as a troublemaker. So it is not clear to me whether your censorship avoidance system will make it impossible for the authorities to determine that you are using any kind of anonymity service. Are you at this level, or?
So yeah, so we are not planning. I mean, our plan. This is work that we're planning to start in the very near future, right? Our goal is to look at the work that has been done in the space of censorship resistance, and to choose whatever is more effective, more undetectable. So it's not that we are planning to. It's not that we have some idea ourselves that we want to put out there. Our plan is to look at the body of work that has been done, and then make choices based on what is working best.
Thanks.
So we have a question from Zoom, and I actually had a small question also from myself. Christina Pepper is asking, in the long run, do you see the need to replace Tor, or do you think there are separate use cases for both systems to coexist? And I'd like to ask, I had some short experience with Tor, and I found it like unbearable slow. I want to ask if you have any data on the user experience for NIM.
Yeah, so the issue is that, so Tor is specifically designed for web browsing, and web browsing is one of the most challenging use cases for this kind of systems, because it's kind of very latency intolerant, right? You have a lot of information that has to go back and forth, and people are really unwilling to wait too long for the page to load. So that's actually a very challenging use case, but you have many other use cases where latency tolerance is a little bit more loose. For example, any financial transactions, blockchains, whatever, people are sending these messages, and then until they appear, there is like some latency tolerance. So if you're adding, let's say, a second to that latency, you're not meaningfully affecting usability. Other applications that are a bit in the middle are, for example, chat. In chat, you can get a 1 second lag and it still be acceptable. Yeah, Tor is basically tackling the most difficult use case, and I don't think in the short term we are going to offer more, we're going to be able to offer a faster service than Tor with these techniques. Maybe in the future we're able to optimize things to the point that this becomes a possibility, but I don't think that's where we are at now. I mean, we're more looking at applications like wallets, chat apps, and other applications where it's not like this web browsing use case that is really, really hard.
Thanks. If there is no other question, I'll also ask. So I see that there is quite a lot of public key involved in all the protocols, right? So will post-quantum cryptography affect the performance a lot? Have you been thinking about it? Yeah,
wow. So I think that's more a question for the colleagues that are more into crypto. I'm more of a traffic analysis person. I mean, my sense is that if the way that I see to deal with this is to use this kind of wrappers with session keys between each of these layers, so that you have that protection kind of for the full stream, like between a node in the first layer and a node in the second layer. They can have like a session key that they share that is ephemeral for the hour, and then use that to wrap around these Sphinx messages, so that you can obtain this kind of protection towards network adversaries.
Okay. There is another question from Zoom. Real-time protocols is very sensitive in delay and order. Can it be used in NIM networks?
What do you mean by real-time protocol? Like gaming, or?
I don't know. Real-time protocol is very sensitive in delay.
I mean, if something is very, very sensitive, that you are already optimizing the kind of without any. That already the internet is too slow, then obviously this is not going to make it better, right? So yeah, I mean, this is the trade-off. The trade-off is that you have some additional latency in order to have a strong privacy properties at the network layer, and that is for some applications this is compatible with the purpose and usability of the application, and for some others maybe the trade-off is not. There is no sweet spot where you can have both things.
Okay, thanks. Let's thank the speaker again. I'll now pass the microphone to Hassam to introduce the session